Enregistré.
Bonne intervention.
C'est bon, ça marche. Merci, remercie.
Okay, so I start now. So for a short presentation of QNC, I think it's nice, it's good to start from the time-dependent Schrodinger equation, the usual one. Time-dependent. So this is a general equation you want to solve. So we know the solution, but the solution is usually written as so where psi x0 is some arbitrary function, whatever. So x, let me just insist, x is in a general space. So any dimension. I wrote x, but it really means that you are in multidimensional space, which is important because QNC is effective in multidimensional space. So that is the solution, but be careful. This is, in fact, a formal. It's a way of writing the solution. Exponential of an operator is a compact representation, but the problem is to compute it. The action of this operator is non-trivial. So, as you know, if you take an operator, you can make its spectral decomposition, okay? Which is the sum of all the is eigenstates, is eigenvalue, and the projector, which I can call like that, for example. Okay? This is a way of expanding. So if we do that with this operator, we can write the exact solution, I say x of t equals sum over all the eigenvalues, exponential minus I t h bar the energy, times phi I of x, and the overlap of phi I with the initial condition, which is some number. So we have the exact solution under the I, okay? If we are able to compute psi x of t by a simple Fourier transform of this quantity, let's suppose that you compute for a given x and for different time. The Fourier transform will give you all the spectrum, for example, as an example. So you can extract the exact energy and also the exact eigenstates just by making some elementary operation on the quantity psi x of t. Okay? Of course, it's very difficult to do that. So it's called, if you want to solve this, it's called quantum dynamics. And this is a very hard, and usually we are not able to do that only in a small dimensional space. 1, 2, 3, 10, a few hundreds in some case. For example, probably the most well-known method is MCDDHF, which has been developed by the group of, I forgot his name, Cederbaum, which is multi-configuration time-dependent R3 fork, which is one way of solving that, okay? But it's hard. Now, the idea of QNC and all QNC method is to make the following remark. You see that this equation, this expression here, if I change t into a new variable, which I can call it t tilde, which is I times t, if I'm able to compute psi x of t tilde, which is sum over I exponential now is t. Okay, now I will make h bar equal 1, because you know that in atomic units h bar equal 1, and we always use h bar equal 1, so I use it right now. If you write, you just replace IT by tilde, and you get that, of course, tilde. And we can forget about the tilde after that, call it T. And you see that if you're able to compute that, you can compute also the same spectrum and eigenstate. Because the Hamiltonian is independent of time, you don't care to work in a real time or in imaginary time. Okay, so QMC works in imaginary time, and we'll compute that. Okay, now it's no longer a Fourier transform you have to do to compute the spectrum, but the Laplace transform. And for example, if you are able to compute that for a given x, you would have limit t goes to infinity 1 over t logarithm of psi x of t will give you an estimation of the ground state energy. This is what this kind of manipulation you can do in order to compute the exact ground state once you have been able to compute that. And the key idea of QMC is that we are going to be able to compute this using stochastic methods, Monte Carlo, in an easy way, in huge dimensional space, millions eventually of variables. And if you want to do that, it's much more difficult, and you can do it only in a very small dimensional space, quantum dynamics. It's large number of people working to try to get efficient algorithm to get that for large dimensional space, but it's a very difficult problem. So QMC is targeting that kind of expression, and there is some very simple scheme to do that. Okay, so how do we do that in a few words? In the new time, imaginary time, my time-dependent Schrodinger equation now is derivative of psi with respect to t equal minus h psi. It's trivial. You just replace that in the original equation. Okay? Okay? And the solution is, of course, exponential minus t h applied to the starting wave function. So, if I want to compute that, that is, if you want in terms of Ket and Bra, is x exponential minus th applied to psi 0. Okay, so I don't know the notation. Okay, and this is the integral over dx prime of x exponential minus th x prime psi x prime 0. So, as I said, we want to compute that for a number of time in order to extract the exact quantities. And to do that, we need to compute this quantity, which is essentially the basic quantity which makes the evolution here. We have to compute that. If you don't use a stochastic approach, it's just extremely difficult. This is in fact a green function, a time-dependent green function. If you make a Laplace transform of that, you would have a standard GW green function in a frequency space, but in a time space, this is this. Here it's a full Hamiltonian. Here it's, for example, the coordinates of all electrons, so it's a very tough. We have been able to compute that only for the hydrogen atom. We have an analytic expression for that, which has been computed in 1980. So it's quite tough. It's not so long time before. Okay, so now just we have to compute this, and we'll do that with Monte Carlo. Okay, that's the main point. So now how do we do that?
So how is the expression of G for the hydrogen atom? Is it an AD expression or?
No, it's a compact expression. It's hard. I mean, it has been gotten by I don't remember the name, in 1980, and it's a big expression that compact. And it's important to note that if you could say that for the hydrogen atom, G is something like that. Plus, don't forget, there is a continuum. There is a discrete part and the continuum part in the spectrum of the hydrogen atom. And look, if you look at the energy, it's in 1/n². And there is an accumulation point in E equals 0. So in fact, if you do that, it diverges. Because of the spectrum here, the excited state, I wrote the principal number of hydrogen atom. If you know that by the spectrum, it diverges. So clearly, of course, G doesn't diverge, but you have a compact expression which gives you that. Okay? So it's a kind of tour de force. Okay.
So there is no expression in the uniform electron gas?
No. No. Would be nice.
Because if you take 2 electrons on a sphere.
Yes, you have it. I'm sure.
Yeah, you have it because the psi are just spherical harmonics and there is no continuum.
Yeah. So it's just a sum to do. Okay. So how we compute that? So this is a fundamental quantity. And all quantum Monte Carlo methods explicitly or implicitly compute that. And what is the basic idea? H is written as the kinetic term and the potential term. We don't know how to compute for an arbitrary time, but we know good approximation when the time is small. So what we are going to do is to write this as a product of operator. Here it's exact because H commutes with itself, so this is exact, of course. And here you introduce some sum over some resolution of the operator of the identity, and this will be written as a big integral between G, but a small time, x, x1, tau, G, x1, x2, tau, to G, up to the last. And this is exact, of course. So we have an analytical expression. Of course, this is right when n goes to infinite, which means that tau equal with tau equal 1/n, and t equal n tau. So tau equal t over n. So if you do that, you take smaller and smaller tau, and you insert your spectral decomposition of the identity operator, you get an exact expression for this quantity, which involves only grid function as small tau. By the way, of course, this is a path integral. Okay, path integral Monte Carlo, for example, is based on that kind of formula. Diffusion Monte Carlo is based on that kind of formula. All QMC methods are based on that kind of formula. Okay, all. Sorry? V, it's a potential of your problem. So for a molecule, we will have sum of electron nuclei and electron. The standard total potential of the system. Remember, X is R1, R2, Rn, where I are position of electron I. It's in a 3n dimensional space. The total potential. Okay. No. This is a total IH. You can write exponential tau A plus B equal exponential tau A exponential tau B if A commute with B, which is the case H commute with itself. So you can write exponential tau H as a product of exponential minus tau H. It's exact.
T has been replaced by tau.
T, T is n tau. I wrote it here, but tau is, yeah, T is tau plus tau plus tau. I'm sorry, I've not been clear enough. So at the end of the day, QMC works because the exact green function, which gives you all the exact properties, can be written as an integral which involves only short time green function. And we have very good approximation of short time green function. And we can sample this short time by Monte Carlo. Okay, so of course we don't know G at small time, but we have very good approximate expression which allows to sample it very efficiently. Okay. Is it clear? I mean, it's self-contained. So you should be able to understand everything if I'm clear enough. That's my problem at this point. Because there is nothing obscure here. Everything is pure mathematics and very simple mathematics. So now, just two ingredients. One, how to sample the short time G. So there's a standard, very easy way, which is inefficient. And in order to make it efficient, we will introduce a trial wave function, which is an approximation of the exact solution. And using a trial wave function, you will be able to compute it efficiently. And so the CPC wave function are used as trial wave function. And the most accurate the full CI CPC wave function is, the better, the more efficient will be the simulation to compute that quantity. Okay, so let's see just the naive way of solving, of sampling this. And after, I will just say the generalization with a trial wave function and the approximation we have to make, the fixed node approximation, which will be the last. Okay, so x exponential minus tau, but now tau is small. H is, as said, the gradient squared plus v of x. Multiplicative operator, a differential operator. So you can write this as exponential minus tau, the kinetic term, that calls T plus V. Right. And now, at short time, we write that as the product this is an approximation because T and V do not commute. So to write exponential A plus B, A plus B, plus a term which is related to the commutator of A and B. Okay? We know that if I write exponential a plus b as a product of exponential, a and b do not commute, so there is an error. But this error, you can show that this is an error which goes to 0 when n goes to infinity. At the end, to get the exact properties, I will cut by tau n times, and we can show that in this limit, this goes to 0. Essentially because this is a tau square multiplied by tau, which is 1 over tau. So tau square over tau equals tau, and it goes to 0. But this goes to 0. So this is exact when tau goes to 0. And now this can be written as x exponential minus tau t oh, I made an error. Here it's minus tau h. H is t minus tau t. Yes. Okay, that's good. It's okay. X prime, exponential minus 2b x. Okay, second x prime. Okay, this is x prime. And this is a local operator. So this is delta x prime minus x second exponential minus tau b of x prime. A multiplicative operator is diagonal in x. And this, you know that this is the kernel of the heat equation. The equation for that is, for this quantity here, is dg over d tau equal Laplacian of g. In fact, it's easy. It's a equation I wrote just before, where v equals 0. Okay? This is, you know that, it's the heat equation. And we know the exact solution of that by Fourier transform. The exact solution of that is g of x prime tau equal exponential minus x prime squared over 2 tau with some effector in one dimension or in any dimension. Like, okay, x minus x prime squared tau is a green function of the heat equation. Okay, do you remember that or not? Oh, it's easy to check. So when tau goes to 0, it goes to the delta Dirac. And when tau goes to, so it is a diffusion of, you start with some heats localized, and time diffusion of the goes up to the constant. So never mind. We know this. So at the end of the day, x, and this is what we have to recall, exponential h x prime is approximated by and it's done. We have an accurate expression of the green function at small time, explicitly, the Gaussian times this quantity. And if you put that in my path integral representation, you have an exact integral, which gives you the exact properties. Okay? So you could imagine, and some people have done that, you can compute this integral analytically. But analytically, it's very hard And we know that when the dimension is large, compute an integral, we need Monte Carlo. Monte Carlo, I recall, is the only method which works when you integrate in a dimension superior to d equal 20, 30, 40, after you have only Monte Carlo, no other method. Yeah, but I mean, you can use quasi-Monte Carlo, for example. Up to 20 can be more efficient than Monte Carlo. You can use special grid of points depending on your problem, etc., etc. But when you are more than 20, you are sure. And here we are talking about thousands and millions of degrees of freedom. So, okay. So now, how to simulate this to make the integrals? This is a transition probability, in fact. This can be interpreted as a probability, transition probability. What is a transition probability? I recall, this is a probability with respect to the final variable. I'm an x. I want to have a probability to go in x prime. This must be positive, which is the case, and the integral over the final all possible value must be 1. 1, we don't care. It must be independent of x. And this is the case. If you integrate over x prime, it's independent of x because it depends only on the difference. So this can be viewed as a transition probability. This is called the Brownian motion. This is exactly this. This is a Brownian motion. So you take your electron and you can choose a new position of your electron with this Gaussian law, which is trivial. It's 1 Fortran line or 10 channel, Camel, Ocam. Camel, comment c'est son truc? No. What is the name of your language? Ocamel. It's 10 line in Ocamel and 1 in Fortran. If you put implicit, okay, I'm stop here. Okay, so this is very easy. And this, what is this? This is like in chemistry, if you write this equation, it's Zc over derivative of psi over t equal V of x of psi. It's like a first order chemical reaction. It's a multiplication of particles at point x. The density of particles at x increase or decrease according to the sign of V. So it's what we call a branching process. If V is negative, the density will grow in time. If the V is positive, the density will shrink in time. So this, you can, at the end, diffusion, Brownian, very easy to implement, and this is multiplication or diminution of a number of particles. So, what are the rules? Let's take a hydrogen atom. You move the electron in time tau with this, and you kill eventually the electron, or you multiply, you make a copy of electrons at the same place according to the potential. And that's it. Monte Carlo program is extremely easy to write. Diffusion, you draw Gaussian number, and multiplication or diminution, okay? That's it for the naive implementation, okay? Is it okay or not? This? No, we are in a probability here. positive integral. No, it's not. Here? Yeah, but this is positive. This is positive. This is a probability. Be careful. It's an amplitude of probability when the time is real. But in imaginary time, it's everything is positive. So it's probability. So it's a very good remark. In quantum mechanics, we have probability amplitude with interference. In QMC, you are in imaginary time, you have probability, and instead of interference, you have damping, because on exponential minus t, e. So you have no longer interference, okay? And this is interference, which makes the problem difficult in real time. Okay, so I will finish soon. So this, the paper, you can look, it's a very simple, H2 plus, Anderson, Jim Anderson, 1976, JCP. It solves the H2 plus system, 2 electrons, the molecule, with that. And it works with a lot of fluctuation, but it gives you an answer. It's the first paper on the molecule with QMC.
So, can I do a remark on this?
Yeah, of course, something is wrong.
It's, no. It's very important because that system is hard. If you want to do the usual quantum the 2 electron system, to tell yourself. But if you try to complete the integrals of that system, it's hard because it's not a dimer, it's not an atom. If you want to solve an analytically the integrals like you do for million atom or H2, it's difficult because it's a file that is still sampling, but are not counted. So they couldn't do it, and only like possible to do it because you don't have to configure integrals. So you configure them by
In contrast with full CI, we have no integrals to compute, only drawing. So now, it's not efficient. Why? Because V is a Coulombic potential. And if 2 electrons, for example, get very close, you have an explosion of the number of, in fact, a total shrink. And if you are close to a nucleus, you have an explosion of electrons, okay? And so at the end, the fluctuations are too large for a large molecule. It can work for 2 electrons, but after it becomes really irrealistic. So so it's an interesting paper. You have another paper by, which is really the most important paper, 1984. One, I think it's Reynolds et al. Where they give the algorithm which works and which is the algorithm which is still used nowadays, which is a basic one. And in this one, we make the following remark. The equation we are solving here is this one. And the solution at large time convert to the ground state exact unknown solution. Okay? And you have this potential which is very weird. What they say is, let's use a tri-wave function, which would be a good approximation of phi 0x. We don't know phi 0x, but we know approximation, R3 fork, CPC wave function, or whatever we want. And instead of using F, we introduce a density F, which is a product of psi t x and psi x t. I don't have the time now and it's to fully justify that, but the key idea is to introduce, instead of psi, we multiply psi by some function, and you have a new density. And of course, it's a few lines of calculation on your paper. You can get the equation for F now. We have an equation for psi. Psi t is some fixed given function. And you find that, and this is a fundamental equation, df over dt equal always 1/2 gradient of F, the same term, the kinetic one, the diffusion one, but there is a new one, which is a gradient term. And a potential, which is now h over psi t of x divided by psi t of x minus 0. It's exactly the same structure, except that you have a new term here. B is a drift term, which is defined as gradient of psi t over psi t, drift term. Which is a central in QMC method. And this is called the local energy. We call it usually EL of x, local energy. So if you give me psi t, for example, Hartree-Fock, I can compute the drift. It's a vector, which is a gradient of psi t over psi t, and I can compute the local energy easily because I have to apply h to psi t, so make the second derivative, the kinetic term, plus a multiplication by the total potential, and this is a local energy. And if you look at this equation, you recognize the evolution of F, the same thing that evolution of psi. And you have a free diffusion term, which is what we got before. We have also, oh, here it's multiplied by F. We have also here, you can see it's a multiplicative operator. The local energy depends on X. This is a new potential. Instead of V of X, we have the local energy of X, just a new potential operator. And the only really new term is this term, and I have no time, believe me, but this term you can easily show by solving the equation df over dt equal, when you isolate only this term, you'll see that this term takes you a Dirac and drift the Dirac. The effect of the equation df over dt equal gradient bf, you can solve it to start from a delta Dirac. If you don't smooth it like this term, what you do is you move it with a drift. So it's the reason why we call that a drift. A drift is a force which, a drift is a change of position, a force change of the speed. So that's the description of name of wording. So now, I just erased this. I'm almost done. Not entirely, but it's okay. I mean, not too long.
Take your time, Michel.
So now, my hydrogen atom, I have one electron. I do exactly the same thing as before. I diffuse with a Gaussian, which is a trivial on a computer. And now I drift it with B times tau. B is a drift vector, and B for tau is the effect of the term. And now you multiply or divide or whatever you kill according to the new potential, which is the local energy. So here it was V of X and no drift. And here it's drift plus new potential energy, local energy. Of course, if you take psi t equal 1, the drift is 0. The local energy becomes a bare potential V, so you recover that. If you take a psi t close to the exact phi 0, what will happen? EL will goes to E0, the exact energy. Here, we call that the local energy, because if psi t is chosen to be phi 0, it goes to the exact energy. Okay? So the closest, the better is your approximation of phi 0. The lowest, the smaller will be this effect of multiplying and killing electrons. And if you have the exact solution, you have no longer any change of number of no killing, no, okay? So you see that I said that because you have huge fluctuation of the potential, it was difficult to make it converge to large system. Now, if you have a good trial wave function, these fluctuations are small, and you can do large molecules. Okay? And the second, the two things in the same shot, kill two birds in one shot, that's the expression, I think. Two birds with one stone, it's incredible. Look at this drift. What is the effect of this drift? Let us write it as 1 square gradient of psi t squared, the same as before. You see that this drift, in fact, if I go in a direction where psi t decrease, the drift is in the other opposite direction. If you go in a direction of psi t increase, the drift also is the same direction. So the effect of this term is to push the electron in the region where the wave function is large. So it's extraordinarily efficient. I mean, here, with the free Brownian motion, the free diffusion, the electron goes everywhere, even far away. The density is constant. Here, if you add the drift, you push the electron where the trial wave function is large, and since it's a good approximation of phi 0, you go where you have to go. In Monte Carlo, it's called importance sampling. And you have no Monte Carlo working in the world if you don't have importance sampling somewhere. Why? Because in dimension 1 million, the space is huge. If you don't help your drawing to go where you have to go, where the integrand is large, you are dead, completely dead. Okay, so you need importance sampling. The importance sampling is here. It's wonderful. So at the end of the day, your program is few lines. You draw Gaussian number, you move the electron, you compute B, you make a small displacement, P for 2, and after you compute the local energy and you multiply. Okay? Now you can tell me, but how to compute the exact energy, for example? So it's a very simple thing, is to see that F, which is psi t of x times phi 0 psi x of t, goes to psi t of x, phi 0 of x. Okay? We saw that we multiply by psi t. We saw that the first equation, phi 0 is a ground state at a large time limit. If I multiply by psi t. So now, if you, for example, take the average of the local energy over the distribution you get at large time, yes, you can see easily this is h psi t, psi t, psi t, phi 0 over integral of dx psi t, phi 0. You simplify by psi t. You use the fact that h is Hermitian, so this is equal to E0. So simply by averaging the local energy over the distribution of electrons you get using these three simple rules, you get an estimate of the exact energy. And you see that in your algorithm, you only need to compute to know psi t. Okay? So you can do it very easily. Three process and an average. And that's it. Okay? And it is very efficient because there is this important sampling, both in terms of sampling of the space and in terms of the average. Because when the psi t is good, you get less and less fluctuation here also. So everything goes in the correct direction. Okay, so I am almost done. This is the basic, this is the algorithm, the DMC diffusion Monte Carlo algorithm. And there's only one point left now, is the approximation we make. So now I'm talking the last point, just to say a few words about what is the problem here. We know that the ground state is positive. If you take an Hamiltonian of a molecule and you compute the ground state, the lowest state of the Hamiltonian, it is positive everywhere. It's easy to demonstrate. It's called Perron-Forbranu theorem, because the Hamiltonian has the structure of the form T plus V. You can show it. It's easy to do. Okay? So this is not the correct ground state for electrons. For bosons, if you have no symmetry, this is exact. And with this, you get, because remember, what I get is a density which is positive. By construction of my algorithm, what I get is a density. I am counting, you know. So in fact, you converge to this ground state, okay? So for bosons, it's okay. And for bosons, diffusion Monte Carlo QMC is the state-of-the-art method. You cannot find a better method. It's clear. It's crashed completely. I mean, it's other methods are. However, if you have electrons, the situation is different. This is not the ground state. This would correspond to the fact, take a neon atom and put all electrons in the 1s. 10 electrons in 1s. That would be typically that. But of course, we know there is a Pauli principle. And there is a restriction on the wave function. You have anti-symmetry property of the wave function. So the true ground state, so this is called a Bosoniquant state. When we make quantum chemistry, we never heard about that. I mean, it doesn't enter the game at all, but it exists. It's an eigenstate of your Hamiltonian. And for electron with a Pauli principle, you have a fermionic ground state, which is formally an excited state of H. You understand that? If I look at all the spectrum of the Hamiltonian, you have states lower than the physical state, which are bosonic. So formally, our physical ground state is an excited state of H, okay? It is a ground state in the symmetry, anti-symmetry subspace, which is higher on energy than the ground state in the fully symmetric space, which is lower in energy, okay? So the problem is, I'm talking about that because the scheme I showed you, you converge to the bosonic state. And you are in a bad shape, okay? So you have to do something. This is called the sign problem in quantum Monte Carlo. This is a problem that you have a diffusion way of solving the Schrodinger equation, which makes you converge to the bosonic state. Okay? So when you have fermion, you have to solve that. And I won't enter in the story of the sign problem, but we have one stable, realistic, and only one solution to this problem right now, which is called the fixed node approximation. The fixed node approximation is fun because even if you don't know the problem, you do it. You don't even know, I mean, during my PhD thesis, the subject was development of an alternative way of doing that. At the beginning of my PhD thesis, I was not aware of the existence of QLC because nobody was doing QLC in Europe. And I rediscovered the fixed node approximation by chance. I mean, why? Because if you do what I say, you take psi t equal psi r3 Fock, for example, we'll construct B gradient of psi t over psi t, energy local equal h ct. You run your calculation and you get the physical quantum state. You don't get the Fermi quantum state, the Bosonian quantum state. Why? Because when you have antisymmetric wave function, you have some place where it can be zero. This is called the nodes. So if you have an antisymmetry wave function, tri-wave function, which will be always the case, you necessarily have psi t which vanish. So this is my configuration space of psi t, the sign of psi t. If I'm here, I will take my diffusion, my multiplication, my drift. But look, here it will be more like that because we are close to 0 for psi t. But look, gradient of psi t over psi t, if psi t goes to 0, it goes to infinity. So it means that if you do what I said to do, your trajectory are completely trapped in the domain where they start from. They cannot go outside the volume of constant sign where they start. Well, okay? So everywhere is fine, except that the zero of the tri-wave function are not exact. They are not the zero of the exact eigenstate. So you solve the Schrodinger equation with new boundary conditions. You say, I solve h psi equal e psi, with psi going to 0, where psi t goes to 0. So you add new boundary conditions which are wrong. So you have an error. This is called the fixed node error. Okay? So now we have a well-defined scheme, the same as discussed before, except that you have to realize that your electrons are constrained to stay in the same volume. And so the energy you get at the end is called a fixed node energy. And you can show, because it's a variational ID, that this fixed node energy is higher. So it's a variational principle. So you made a variational error, like in variational method, except that the energy is much better than in the standard CI stuff. Okay? So now, that's the reason why we need to have the better tri-wave function in order to decrease the fluctuation, but we also need to have tri-wave function with good nodes. It's better to have a tri-wave function which has good nodes and which is not very good with respect to the total shape, but than to have a good tri-wave function, but with bad nodes. I finish with one drawing. 1 hour, no, 1 hour. Okay. So my drawing will be the following. Let's look at 1D problem. The exact wave function will be, okay, I start, so it's a psi of x. So it's my wave function. So I have a starting psi t of x. Let's suppose I have chosen a psi t of x. Okay? What is going to do fixed node DMC? He will fix the zero and in this domain, he will solve the Schrodinger equation. For example, he will say like that. Okay, this is a phi zero exact fixed node. The solution of the Schrodinger equation in each domain, which pass through the nodes of psi t. And this is approximate because the exact wave function does not have these nodes. So, for example, the exact wave function could be, usually it's very close, but hop, hop. It will be almost the same as your solution obtained by fixed node DMC. It will differ mainly close to the nodes because they are free to have different nodes. And this is the reason why fixed node DMC are so good energies. This is because the fixed node wave function is very close to the exact one, except in the region where the wave function is small. So you can see that the error comes from here. And the error is small because the wave function is, exact wave function is small in this neighborhood. So this explains why results are so good. The drift diverge at the zero. So because of the drift, you're right. So nodes are infinite barrier, infinite repulsive barrier. So this is because of the drift, the nodes are imposed. Okay? The density here must vanish at the nodes of psi t. There's no choice because when the electrons goes to the nodes, they are repulsed and they cannot go through the nodes.
So in a computer, they can go through the nodes, but you keep them.
I mean, they go through the nodes, and you see when tau goes to zero, they can no longer. So you extrapolate. At tau finite, you have a probability to go through the node because it's a finite step.
If one impose this approximation, we kill them when they go through the node.
But sometimes they can go 2 times. So plus, minus, plus, so you don't know that they have gone. If the sign of the wave function change, you know that they went through the nodes. But if you have twice through the nodes, you don't know. So sometimes some example where you have that. But okay. So I think it's so the CIPC. Can you show the no? You remember the graph of the water molecule?
Yes.
It's possible to.
Do you see my screen? No?
Yes, well, this one, yeah. This is summarizing what I said.
Is it possible to larger?
Larger?
No.
Wider. Wow.
Wider. Okay, let me see.
Non. Ah, ouais. Oh, ah. Pourquoi ça change tout le temps?
Attends, tu m'as dit plus wide. Je vais zoomer.
Ouais, c'est parfait, c'était parfait. Voilà, super.
Le wide autour.
Mais plus bas. Super, merci. Stop.
Ne touche pas. C'est bon?
So, water molecule at the equilibrium. Energy in atomic units. In green, this is expected to be the exact answer, which means solving the Schrodinger equation. Let's talk in terms of full CI. The full CI in an infinite basis set. So the exact solution of the Schrodinger equation in quantum space. Okay. Here, this says the basis set U. So it's a Dunning basis set standard, augmented V and Z, double zeta, triple zeta, quadruple. These are the full CI results here with the double is too high. The triple is here with a triple basis set, quadruple. So these quantities, we computed them, and this one is from a Mexican guy in a few years ago. He made a huge program to compute it because the full CI is huge. Okay, and of course they are expected to extrapolate to the exact answer. This is what they do. And now, what you see here, of course, is the DMC calculation, the energy obtained with a DMC calculation, with a tri-wave function, which has basically the nodes of this full CI wave function. So the nodes are fixed. So the nodes of the full CI solution. The energy is much lower than the full CI one. So this is why I like to call that a post-full CI method, because in the quantum chemistry course, they always say that full CI is the top. But here it's more than, it's better than full CI. And you see there is an error bar, which at the scale of the problem is okay. And since the nodes are not exact, if the nodes were exact, we would have this. If for each basis set we would be able to construct the exact nodes, we would have no fixed node error. This is a fixed node error. This is a fixed node error. Okay? And you can extrapolate, and since the energies are lower, you can get a better value, extrapolate value. And the value we got is the best value of the literature, the more accurate one. And it is in agreement, in full agreement with the experimental, estimated experimental value. Because the notion of experimental value is always, you have to be careful with that, because there is no experiment to get the non-relativistic fixed nuclei. We have to extract it from experiment. Okay. Okay. So that's it. I think it's over. It's 1 hour. I'm sorry.
Thank you, Michel. Do we have any questions for Michel? No? Okay.
Did you understand? Yeah. Something? Yeah. No? There are many, I mean, the point is usually we are not so accustomed to stochastic process. Lots of algebra and math course.
Yeah.